Hey guys, welcome to another video of quantum field theory. In today's video, we'll be deriving the Hawking effect, which is a pretty cool effect in physics. So, we saw in the last video that in flat space-time, an observer with a constant proper acceleration will actually experience a temperature being caused by radiation in what an inertial observer sees as a vacuum. Now, a good question is, can this idea be extended to curved spacetime? Because we know that objects in curved spacetime that don't fall down. So if you have like a curved spacetime and you have some object, oh, this is a terrible depiction of curved spacetime. Spacetime is intrinsically curved. So if we were to have curved spacetime, so here we have t, here we have x, right? And say here's a geodesic in curved space-time. An object that isn't falling will have some world line that looks like this. So this world line over here is going to have what's called a proper acceleration because it's not traveling in a geodesic on curved space-time. So if objects in flat spacetime that have proper acceleration experience a temperature, maybe objects in curved spacetime that have a proper acceleration, meaning the objects that aren't falling down, also experience some temperature. And it turns out that this is true for the spacetime around a black hole. So let's actually make that idea more concrete. So here I have written the Schwarzschild metric over here. This is the metric for a spherical, non-rotating, non-charged mass. An important aspect of this metric is that it applies to not only black holes, but for any spherical symmetric body. However, for this video, we'll be working with the case for black holes, since the arguments that follow will pertain to only black holes, for reasons that we'll get into later. So, here we have the Schwarzschild metric. A cool thing to see is that as r approaches infinity, the metric actually behaves like the Minkowski metric, meaning that it's asymptotically flat as the radial distance increases. Here we are considering just two coordinates, t and r, so we are dealing with one physical dimension, so we are not going to be dealing with any angles in this video to simplify the calculation. Now, we know that in quantum field theory, we have something called the Klein-Gordon equation, which is this equation right over here. And this can be written like this for Minkowski spacetime. And this equation is very convenient for us because it allows us to expand our field in a mode expansion. And we all know what a mode expansion looks like. But with this metric over here, we can't really expand the field in a mode expansion. If we were to plug in the metric component, because here is going to be g naught, and here's going to be g11. If we're to plug these components into our metric, we are not going to have a homogeneous differential equation, meaning that we cannot expand it into a mode expansion. So basically what I'm saying here is that we want to change this metric to look as much as the Minkowski metric as possible. So here is the Minkowski metric. It's dt squared. And we want to morph this to look like this. So perhaps a change of coordinates can achieve this. So we want to make new coordinates where we'd have the line element equals some factor times dt squared minus dr asterisk squared. And we're going to call r asterisk the tortoise coordinates. So we want to define some new coordinates, t, r asterisk, or really the only new coordinates r asterisk, where we can write the metric like this. This metric is going to be analogous to the flat Minkowski metric. It's going to be what's called conformally flat because it's the exact same thing but we are going to scale it by a function. So the question now becomes, what is the value for this r coordinate? Like, what coordinate transformation do we actually have to do to get the metric in this form? Well, it's pretty simple to solve for that. All we have to do is equate the two metrics together. So we have to say that 1 over 2m over r dt squared minus dr squared over 1 minus 2m over r equals f of r dt squared minus dr asterisk squared. So now what we want to do is just factor out the 1 over 2mr. That's going to give us 1 minus 2m over r times dt squared minus dr squared over 1 minus 2m over r squared. We have to square this so that when this is multiplied, we get just one factor down below. And then now we can clearly see what r conjugate has to be. F of r, we can match that with this over here. And then we can match r conjugate or dr conjugate squared with this over here, implying that our tortoise coordinate, our asterisk, is going to be equal to dr over 1 minus 2m over r. Oops, that has to be dr conjugate. So essentially, this is what our tortoise coordinate, or the differential form of the tortoise coordinate, is going to be. And by using this, we can write out our metric in a conformally flat way. But the question that, this begs the question, what's the value for r conjugate by itself? Well, we can also find that pretty easily. So we know that so if dr conjugate equals dr over 1 over 2m over r, that means that dr conjugate over dr is going to equal 1 over 1 minus 2m over r, right? So what we can do now is we can just do an integral over dr conjugate over dr with respect to r on both sides. We can write out 1 over 1 minus 2m over r as 1 over r minus 2m over r to have them have a common denominator, and that's just going to be 1 over r minus 2m over r. So that's 1 divided by r over 2m over r. Keep, change, flip. It's just r over r minus 2m. Alright? So this integral is just the integral of r minus r divided by r minus 2m dr. Now we can let u equal r minus 2m. This means that du equals dr. So you can write the integral as the integral over r over u du. Now since u equals r minus 2m, this means that r equals u plus 2m. This is just the integral of u plus 2m over u du. And that's just going to give us the integral of 1 plus 2m over u du. And that's just going to give us u plus 2m natural log of u. Now since u is r minus 2m, that's just r minus 2m plus 2m natural log of r minus 2m. So that's our answer to the integral. So the integral over dr conjugate over dr, and then dr equals r to m. And this, of course, is just going to give us our conjugate if we were to integrate it. And technically speaking, we should have a plus c. We could choose our value for c to be 2m to cancel out with this 2m over here, or we could just choose it to be 0 if we'd like. But the main idea here is that our tortoise coordinate, our conjugate, can be written as r minus 2m plus 2m natural log of absolute log of r minus 2m plus c And as R approaches to M, which is the event horizon of the black hole, we get a divergence, right? Because the natural log of 0, infinity, right? Because natural log is log base e, and you're asking e to the what equals 0. So you're actually approaching minus infinity because, like, 1 over e to the x, the limit as x approaches infinity equals 0. So we are approaching minus infinity as r approaches the event horizon. Or in other words, the limit, we could just get rid of this 2m if we'd like, is 2m of r conjugate equals minus infinity. So this means that as the geodesic approaches the event horizon of the black hole, it's actually traversing an infinite distance in the tortoise coordinate. And that's why it's called the tortoise coordinate, because to travel a finite distance, it's traveling an infinite distance in the tortoise coordinate. So it's traveling kind of pretty slow because it's an extended distance when over a small distance, if that makes sense. The tortoise coordinate still has that singularity at 2m, right? Because if you look at the metric over here, the metric for the tortoise coordinate, at r equals 2m, the tortoise coordinate, this is going to be dr asterisk. So dr asterisk. At r equals 2m, we still have that singularity over here. And this is telling us that the tortoise coordinates only cover the region of space-time outside the event horizon. An observer that is hovering outside of the black hole, we know that that observer never sees anything fall inside of the black hole due to time dilation and length contraction. And since the tortoise coordinates only cover the outside of the black hole, this means that tortoise coordinates are the suitable coordinates to describe an observer hovering outside the black hole. There's a nice analogy to this, because we know that in flat spacetime, we know that there are inertial observers, and the inertial observers see no horizon, right? And these coordinates, the Minkowski coordinates, t and x, y, z, these cover the entirety of the manifold, albeit the manifold is flat. And then we have Rindler. You have Rindler coordinates, or Rindler observers. There is a horizon, and the coordinates that they use is nu or n, epsilon 1, epsilon 2, epsilon 3. And these only cover some small region of the manifold. The Rindler observer never sees anything cross that horizon, so their coordinates only describes a subset of the entire space-time. So since the tortoise coordinate has that horizon at r equals 2m, because there's a divergence there, that means that the tortoise coordinates won't cover the entirety of the space-time region, right? Because we can't really have a negative, like, if you have r is less than 2m for the tortoise coordinate over here, we're going to have a natural log of some negative number, which doesn't have any real value. So that's why the tortoise coordinate will describe an observer that's hovering outside that black hole, because the tortoise coordinate doesn't cover the entire manifold, and the observer won't see events that cover the entire manifold. They'll only see events outside the black hole. So we now have a checklist. We now have found that the analog of a Rindler observer is going to be the tortoise observer, or a turtle observer. So what's going to be the analog for the inertial observer? Well, to do that, we'd have to make a coordinate system that covers the entire manifold, since the inertial observer will see events that cover the entire manifold. They will see events that happen inside the black hole. So a coordinate system that can describe an infalling observer in a black hole spacetime are the Kruskal coordinates. And here is a recipe for how to build the Kruskal coordinates. So first of all, we want to define the following like cone coordinates, u bar equals r asterisk minus t, and v bar equals r asterisk plus t. This is analogous to the last video where we defined the Minkowski like-cone coordinates as x minus t and x plus t. And we will call these r asterisk minus and r asterisk plus later on in the video. And these are really just the tortoise like-cone coordinates, by the way, but we're going to call them the falling like-cone coordinates for now, since they'll be used to describe a falling observer later on, after we do some things like building the metric first. So then we build the metric. Doing the metric transformation, we'd get this for the metric, or really it's technically speaking the line element. And we can see that for r equals to m, here we still have that weird metric. It still gives us 0, which doesn't really make much sense. So we're not quite done yet. We have to define some new coordinates again, and we're going to call these new coordinates, we're going to call them u and v. So u and v, and they're functions of u bar and v bar. And next we build the new metric with the new coordinates via a coordinate transformation, and I'll give us this right over here. And we see that the metric is no longer singular at the horizon, because when r equals to m, this becomes 1, and this becomes 1. So the metric becomes minus du dv, which is a good thing. So the Hawking effect is really just the Unruh effect, but more generalized to curved spacetime. Because we have the same shtick, we have one observer that has 0 proper acceleration, another that does have a non-zero proper acceleration. Like this frame describes, or it's most suitable to describe, a geodesic on that spacetime manifold. And geodesics, they have the property where the derivative of the tangent vectors, dot product with the tangent vectors themselves, should give us 0. But since we are dealing with an intrinsically curved spacetime, this has to be 1. Because our spacetime is extrinsically flat, which means that the second derivative vector should equal 0. And this is just the 4 acceleration, pretty much. So the 4 acceleration of a geodesic is going to be 0, meaning that there is going to be 0 proper acceleration. Even though they're falling, but since the space is curved, it all works out. So this is where the actual quantum field theory on curved spacetime comes in. So remember that for curved spacetime, we want to specify the metric tensor components, this over here, for the Klein-Gordon equation. So from the Kruskal and tortoise coordinates, the metric for those coordinates, we can infer the metric tensor components. So here GUV equals GVU, which equals this. And here GR conjugate minus equals GTT, which is equal to this. And we can infer these from the components of the metric, or what's it called? The line element. So yeah, we now have this over here. And all we really do now is just plug these values into the Klein-Gordon equation. So let me again just write out the generalized Klein-Gordon equation. Again, there should technically be factors in front of that, like determinant of g, things like that. But for our metrics that we are considering, all those factors will just come out to be 1. So we have this over here. Let's actually start out with the tortoise observer, since that's the easiest one, right? Where you are going to have v equals 0. That's just gt, or not to say g, partial t squared, times the first component, which is 1 minus 2m over r, and then minus g r conjugate squared, and then 1 minus 2m over r, plus m squared, phi equals 0. We can see how we can just factor out the 1 minus 2m over r. That gives us with this, minus this, plus m squared, phi equals 0. And this is going to imply that partial t squared minus partial r asterisk, sorry if I say conjugate, I mean asterisk, squared plus m squared phi equals 0, which looks exactly like our Klein-Gordon equation for flat space-time. So this is going to be the formula that we are going to solve for the tortoise observer, the tortoise coordinates. Now, can we do the same thing for the crucial coordinates? Well, for the crucial coordinates, things get a little bit more complicated. So again, we start off like we did before, with partial mu, g mu nu, plus m squared phi equals 0. We can expand that out. It wasn't clear. Like, it's just like for convenience, g naught naught, we take it to be well, for the tortoise coordinates, we took g naught naught to be the time entry, and then g11 to be the r asterisk entry. Similarly for the crucial coordinates. Now, if we check the crucial coordinate line element, we see that we do not have any du squared or dv squared term in the metric, which means that we do not have any g naught naught term or a g11 term. So those go to 0. And since we have a du dv term, we should, technically speaking, have a 2 partial not partial 1 g1 naught term in the Klein-Gordon equation. If that isn't clear to you guys, watch. I have a couple of videos on. I have a couple of videos of the metric tensor components. I think I may have talked about that somewhere in my tensor calculus series. But basically, we have to include the diagonal or the off-diagonal elements of a metric tensor. For most cases, those are 0. But for the crucial coordinates, the off-diagonal elements are not 0. So we need to consider those. So doing that, we'd have 2 partial naught partial 1. And then g1 naught is just going to be this over here. So, well, this was going to be g1 or partial 1 partial naught. But to make it a bit more clear, we're going to say partial u partial v. So then we can say that then we should have plus m squared phi equals 0. And then what we can do now is multiply the 2's together to get 4m over r partial u partial v exponential r over 2m minus 1 plus m squared phi equals 0. So now what we can do is factor. Actually, well, before we factor things out, we have to take m to be 0, because we can only factor things when the mass is 0. So for these cases over here, the mass should be 0, right? Because we factored these terms out, but we can only factor them out if the mass is 0. So we are dealing with the massless scalar field. So doing that, we then have 4m over r partial u partial v exponential of r over 2m minus 1, and then times phi equals 0. This implies that partial u partial v phi equals 0, since this term over here, this times this, is never going to be 0, meaning that partial u partial v has to be 0. And this is the Klein-Gordon equation. I know that doesn't really look like it, right? Because usually we would expect it to be partial u squared minus partial v squared. But we have partial u partial v multiplied together. But it is still, technically speaking, a homogeneous differential equation. So what is the solution to this kind of equation? Well, it's actually not that complicated. It's saying that the derivative of the function with respect to v, and then take the derivative of that again with respect to u, should give us 0. If the derivative of this with respect to u gives us 0, that means that this cannot depend on u. And then we can switch it around. This is the same as partial v partial u phi equals 0, which means that this cannot depend on v. So this means that our function phi can be written as a of u plus b of v. So we're separating our function into 2 parts, but instead of them being multiplied together like for the other case, instead they're being added together. And this makes sense because partial v v would then just be partial v b of v, and then partial u of that would give us 0, since this cannot depend on v by definition, or it cannot depend on u by definition. So we can separate our function into two functions that are added like this, and that is the solution to our equation. But to make it convenient for us, we can take a of u and b of v to be exponentials. So a of u can be the integral over the momenta, and then for b of v, it's the same thing, but now it's going to be e to the minus I k v plus a conjugate k e to the I k v. So we are going to define the two functions like that. And actually for b of v, we're going to let the momenta actually be negative, or really it's still positive. I'll explain in a bit. So here we're going to have negative k, and the momenta, or the energy, will run from 0 to infinity. So why do we define the mode expansions this way? Well, to understand why, you have to first look at the mode expansion of the quantum field in the tortoise coordinates. So for the tortoise coordinates, here is our mode expansion. You can see that we used b of p and b conjugate p for the coefficients, because in the last video, the non-inertial frame, the accelerating frame, we used b of p and b conjugate p for the mode expansion. So since the tortoise coordinates describes the an accelerating frame, a proper accelerating frame, a frame hovering above the black hole, that's why we will still use b of p and b conjugate p to stick to the analogy. Analogously, we are going to be using the a of k and a conjugate k for the crucial coordinates, because the crucial coordinates will describe a frame that's a geodesic, that's inertial. And just like in the last video, we used a of k for the inertial frame, that being the Minkowski frame. So here we have the tortoise expansion, and just like before in the last video, we can split this into two parts, a positive frequency part and a negative frequency part. And then what we do now is we combine them under one integral by changing some signs a little bit. This is done in the last video for the Minkowski and Rindler fields, by the way. So it's completely analogous. And then we define the Lycone coordinates for the tortoise coordinates, and the tortoise coordinate, the Lycone coordinate, is defined as r asterisk plus or minus t. And these were the u bar and v bar that we saw before. So this is actually why we define the crucial mode expansion like that, because if you scroll down, here's the crucial mode expansion. You can see that this is the a of u, and this is the b of v. Here is the tortoise expansion, and it looks a lot like the crucial expansion. So really, we chose the crucial expansion in such a way that when we wrote the tortoise coordinate in the tortoise coordinate mode expansion, we can compare them easily because they look the same. So to clarify something, this the crucial modes a of k and a conjugate k, these modes will describe an infalling observer, right? Or can describe a falling observer. And then b of k and b conjugate k, these are going to describe an observer hovering above the black hole. So a of k acting on the vacuum state will give us 0, and we will call this the crucial vacuum. And then b of p acting on the tortoise vacuum, so I'm going to call it 0t, equals 0. So the whole shtick here, the basic idea is that if a of k does not equal b of p, this implies that the two observers, the crucial observer and the tortoise observer, will see a different number of particles. because when BFP will act on what the crucial observer calls a vacuum, it might like give a state that has like 10 particles or 20 particles or whatever number of particles, right? As long as AFK does not equal BFP, that implies that there's going to be a disagreement. So basically, if we have some black hole, oh, I can't draw a black hole on a black screen. So if we have a black hole, a falling observer might say, like, let's say that for the falling observer, they see a zero amount of particles. So they say that they are in the critical vacuum. But then some observer that stays at a constant radius outside the black hole, they might say that there is a non-zero amount of particles. So they say that there's a non-zero amount of particles. They each have different vacua. And the observer hovering above the black hole will see a non-zero amount of particles because of his proper acceleration, basically. So he will see particles present in the black in what the inertial observer sees as zero particles. So again, like before, we can make this more concrete by actually comparing the coefficients in the crucible frame and the tortoise frame by using the Bogle-Yubov transformation. So let's do that right now. Also, another important thing is that there should be a negative sign right over here. So these should have negative signs in them, because in order for us to put this under the positive frequency integral, we have to change the sign inside of the coefficients for the second term. So just want to note that. So now what we can do is, since these fields are equal to each other, both observers agree on the field, that means that we can equate each part to each other. So that is going to imply this relation right over here. So the positive momenta parts will equal the positive momenta parts, and analogously for the negative one. So using some arguments here, we will obtain this right over here. Again, this is the exact same thing as the last video. We're just replacing u with we are replacing x minus with u, and we are replacing x tilde minus with r asterisk minus. So using some more arguments, we get this, and then using some more arguments to get the Bogle-Yubov transformation, we can identify this right over here. So we want to calculate this quantity right over here, because if we integrate this quantity over the momenta over 2 pi, that will give us the expectation value of the number operator, or of the tortoise number operator in the crucible vacuum. So it's going to give us this right over here, and this is a quantity that we are interested in calculating. That's equivalent to this right over here. So the main quantity of interest is what's on the inside right over here. So how do we calculate that? Well, just like before, we have to first explicitly define what f of minus kp is. It's going to be this right over here. Recall these relations over here. This should actually be a u and v. And these should have bars on top. So these are the crucible coordinates that we saw earlier. So since the integral is over the tortoise coordinate, you have to convert the crucible coordinates to the tortoise coordinates, which is pretty simple to do. Note that again, u bar was equal to is the same as r asterisk minus, and then v bar is equal to r asterisk plus. So what we have to do here is to just plug in u right over here. So doing that, we are going to get exponential minus ik, and then we're just going to plug in our value for u written in terms of the tortoise coordinate. And then since we are multiplying these together, we can just add them. So we are going to have an exponential of minus ik 4m e. We don't really have to do parentheses there. The i's, or the negative signs, cancel out. So we have 4ikm, so 4ikm, and and then e to the minus r asterisk over 4m, and then minus I p r asterisk minus. And then we use this property over here of the f function, and then by doing the thing that we did in the last video, where we talked about how like the integral of like the Bilkuibov coefficients multiplied together will give us like 1 in the end. We use that property, and then we'd get this equation right over here, and then we divide both sides by this term over here. We get this. If we let p equals p prime, we have a divergence here, but and that means that we have 2p over here. That will mean that 0 to infinity of dk over 2 pi k over p, and then this over here is going to equal delta 0 over e to the 8 pi m minus 1. Now, of course, the divergence is a problem. If we were working on a finite space-time volume, we can just kind of ignore this right over here. And then we can, and we're done here. This is equal to the expectation value of the number operator and the in the torus coordinate for the crucible vacuum. So this tells us that the tortoise observer, so if you have a black hole over here, and they have the tortoise observer right over here, the total observer says that there is 1 over e to the 8 pi m minus 1 particles in which the crucible observer that does not have a jetpack because he's falling sees 0 particles. So in the crucible observer's vacuum. So yeah, and technically speaking, again, we should technically integrate over the momentum here, which makes things a little bit more complicated. But if we kind of ignore the integral over the momentum by now, here is the kind of the main part of the calculation. And then again, we can use that formula that we saw in the last video, where e to the, I think it was over t minus 1, that tells you the probability that some number of particles has some energy, and that's going to equal 1 over e to the 8 pi m minus 1, or we assume that they're equal to each other, which is an assumption. And this is the Bose-Einstein distribution, by the way. And that will imply that e over t equals 8 pi m, meaning that, and since e, well, we should have a p here. Where did the p go? Yeah, we had a 2p here, so there should be a p here. We can't forget our p's. And since p equals e, this becomes, this will just come out to be t equals, it's 1 over 8 pi m. And this is the Hawking temperature. And that, my friends, is how you derive that. So yeah, we're pretty much done here, but we have to address the elephant in the room. So we use this property, which is not obvious. In the video and on the Unruh effect, we used the same property, but instead we had a p pi over a. You can kind of see that 1 over a is sort of analogous to 4m. Yeah, so the Unruh temperature, by the way, was a over 2 pi. So you can see that a kind of equals, it's analogous to 4m, or 1 over 4m. So we have to prove this property over here. And to prove that, we have to do an integral. A proof of this equality right over here. We can prove this based on a change of variables technique. We can define some new variable z, where z equals the torus coordinate plus I pi 4m. And then this means that dr asterisk equals dz, which is pretty convenient for us. And we can rewrite our conjugate like this. And then by just plugging some things in, I know it's kind of hard to see here, things kind of got squeezed a bit, but by substituting some things in and focusing on this part over here, we would obtain this right over here, and then we can move the e to the minus 4 pi m that came from this part over here to the front, since it doesn't depend on z at all. and that will give us this right over here. I know it's kind of a bit of lazy writing. This is a dz over 2 pi. But yeah, we get this over here, and this I pi over here, if we're wondering what happened to it, this is just the equivalent of e to the I pi, and e to the I pi is just -1. So, and then if you guys can't see, this is a negative sign over here. I should probably write that a bit more explicit. That's a negative sign right over there. And we can see that this is just e to the 4 pi mp f of minus kp, because if here we had a negative, if we change k to minus k, that'll make it a positive. So that confirms that formula right over there. And yeah, so because this is going to be f of minus kp, even though it's a different variable, it's still the same function. So that's a quick proof. There are some more complicated proofs that use complex analysis. I think the quick proof is more suitable to make this video not too long. So with that being said, that's pretty much it. There are some more things. Oh, one important thing is that we calculate the Hawking effect. There are two things called the Hawking effect, I should start saying. In Hawking's original paper, what he did was looked at a collapsing spherical body that becomes a black hole. And he looked at the space-time before and after the black hole forms. And essentially, the vacuum states will change after the black hole forms, which will lead to the creation of particles. But the subtlety here is that particles aren't really being created, and they're actually coming from the black hole, sort of. Or in other words, those particles already existed when the black hole was forming. So what I'm trying to say here is, what's the calculation for the Hawking effect? It's a relatively quick calculation, but it's physically distinct from how Hawking did it in his original paper. You get the same answer, but here we consider the two different observers within the same space-time, but for the original paper, he considered one observer with a changing objects within a changing space-time, sort of. So yeah, that's an important subtlety, and we will be doing we will be showing the original calculation in a future video. So that's it. Thanks for watching, and have a great day. Bye.